another harmonic oscillator that we can talk about is the simple pendulum. So this is really just a mass on a string as opposed to a mass on a spring. And you all know, you've all at some point in your life seen some form of a pendulum, something hanging and it oscillates back and forth. And if you think about its motion, now you can see that it is harmonic motion. Let's see if it should be harmonic motion. So let's see, we could describe it as a mass on a cable, and it's kind of moving in this sort of curved arc like that. The forces on the mass, we got mg down, and we've got the tension up. So there's a lot of ways to analyze the simple, or the pendulum to see the motion. Let's go with this. Let's just think about when we're at a small angle theta, we can have our gravity, think of it as part of it is along the length of the string, that's mg cosine theta, and then a little bit of it is pulling along the arc, mg sine theta. And then you can sort of think of it in terms of theta or think of it in terms of x. You'll get there the same way. But what we want to think about is Newton's law, is the sum of the forces equals ma. So now let's pretend that this downward direction is kind of like the x direction. And let's call it max. And we can see that this force pushes this way. Now, of course, gravity cannot create a force truly in the x, but it's approximately in the x when you have this little angle here. So we can call this minus mg sine theta. And then for small theta, when sine is small, sine theta is about equal to theta, which here is about equal to the distance we've moved x over the length of the pendulum. Okay, so we're doing some quick geometry here. But the reason is, if we put all that together, you get that minus mg x over L, so this is your position away from 0, L is the length of the string, equals mass times acceleration in the x, and we cancel the masses, and we see this form of the equation that we know, I've told you, gives us simple harmonic motion, and that is minus g over Lx equals ax. That is simple harmonic motion, and we know what the frequency is going to be. The natural frequency is going to be 1 over 2 pi the square root of whatever is in front of the x, which is g over L. So a pendulum moves, interestingly, in a way that doesn't depend on the mass. The only thing that the frequency of the pendulum depends on is the length, well, the gravity, which of course on the Earth is constant, and the length of the pendulum, the length of the string that makes the attachment. I can kind of show you that. You can kind of get a feel for how fast this pendulum goes. And that's only due to its length. And if I add a lot more mass to it here, sort of double the mass, and you can see it goes at the same frequency, same natural frequency. So it really doesn't depend on the mass. Now it does depend on the length, but unfortunately it's the square root and I can't do much to the length. To get something really noticeable, I'd have to have a much longer pendulum, and I really don't have anything. Oh, I forgot. Well, I have this one. So this is our pendulum that goes all the way up to the top of the building, which is about 30 feet. So here we're increasing from L is about 1 foot down to L is about 30 feet right up here, okay? And what that does is has a really big effect on the pendulum. Where this one moves sort of that fast, this one takes several seconds to make a single period. Like that. So there it is. Both of those tell you that this is correct. 1 over 2 pi squared of g over L.